So welcome everybody, wherever you are logging in from. We are continuing our Atto Fridays Seminar Series this week. And we are very pleased to announce that we're going to have a very distinguished speaker talking today, who is Professor Anne. She is a Swedish-French researcher in Attosecond science. In fact, she was one of the pioneers in our field, and she helped establish the field. And she defended her PhD thesis at the Université Pierre-Marie Curie, Paris, in 1986. She was employed as a researcher at the Commissariat à l'énergie atomique et nucléaire, France, until 1995. Recently, she moved to Lund University, Sweden, and became full professor in 1997. Her research has been centered on the process of high-order harmonic generation in gases. And she has, in fact, contributed to some of the main discoveries in the field, really seminal work. And currently, her group works on Attosecond source development and optimization, as well on applications, for instance, the measurement of photoionization dynamics in atomic systems. So it's really a pleasure that you accepted our invitation. We are honored that you were able to join, and please feel free to start whenever you would like to. We're ready to go.
Thank you very much, and thank you for the invitation. So let me share my screen. Okay, so I'm going to focus actually on application of Attosecond pulses today, and application in looking at electron dynamics in photoionization of atoms. So this is the outline of this talk. I will discuss the method which uses the Attosecond pulses and the Rabbit technique. And then I will discuss three applications, three processes that we have studied. First, photoionization of xenon in the 4D shell, then photoionization of helium close to an autoionizing resonance, and finally, photoionization of helium using short Attosecond pulse trains. So let me start by the method, and first of all, the generation of Attosecond pulses. Attosecond pulses are generated when you focus a femtosecond laser pulse in a gas, and you obtain in the time domain a train of Attosecond pulses. In the frequency domain, this corresponds to a spectrum of odd order high harmonics. This process needs first a strong laser atom interaction, which is described by well-known model, three-step model, where electrons first tunnel through the potential barrier, which is lowered by the laser field, the intense laser field, and then electrons are driven away, come back, may recombine back to the ground state, emitting a short light pulse in the extreme ultraviolet range. And the second condition, which is necessary to get this radiation, is that you need to achieve phase matching. This is a nonlinear optical process, and usually it is achieved by because at the same time as you have high order harmonic generation, you have also partial ionization of the medium, and this compensate for the dispersion in the medium, and you can achieve phase matching. Now, what is important to understand is that these Attosecond sources generated by high-order harmonic generation in a gas are extremely versatile. You can find very compact system, very large system. This is still the same process, and this is due to geometrical scaling of the interaction, which is represented on this slide. If you consider a certain geometry with an input energy, you focus your laser into a medium certain length with a certain density, and you get some output energy, then you can scale up or scale down this interaction. You scale by a certain parameter the input energy, you focus over a longer focal length, you get a larger focus, you use a medium's length which is multiplied by the same scaling factor, you use density which is divided by the same scaling factor. And then this interaction is really the same as the previous one. There is really an invariance of the wave equation describing generation of harmonics in a gaseous medium. And the output energy that you get is equal to the same scaling factor times the original output energy. In other words, your conversion efficiency is scaling invariant. And this really explains the diversity of the sources that you can find from very compact sources, as you can see here, where you have a laser, which is an optical parametric Chirpers amplification system, which is just on one optical table. And this is the harmonic generation setup with a rather tiny gas jet. And this laser system provides only a few microjoules, so you need to have very tight focusing. And here on the right, you have, on the contrary, a very long beamline. This time the laser system is in another room. It comes from through the tube here. And here we have, we applied very loose focusing geometry in order to have very intense harmonics. Now, in addition to this geometrical scaling, there is also a wavelength scaling, excuse me, of the source. If you use longer wavelengths, then you can get a higher photon energy, as has been shown, for example, by the group of at University of Colorado. And in addition, there is now a lot of research to generate attosecond pulses with not only linear polarization, but also circular or elliptical polarization, and even with orbital angular momentum. So this is the first part of the tool that we need to study photoionization. The second part is laser-assisted photoionization, which is really a cornerstone of our research in attosecond science, which was pioneered a long time ago in the group of Pierre Agostini. Laser-assisted photoionization is at the basis of the two main techniques which are used to characterize attosecond pulses. The Rabi technique to characterize attosecond pulses in a train, and the streaking technique to characterize single attosecond pulses. So laser-assisted photoionization is you expose an ensemble of atoms or molecules to the combination of attosecond pulses, either in a train or single, and a probe field. And then you study the electrons which are emitted in the process. Now, in this rabbit and streaking technique, you basically assume that the electron wave packet that you detect is a good replica of the attosecond pulses that is used for the excitation. So by looking at these electrons, you can actually retrieve the characteristic of your attosecond pulses and even the characteristic of your probe field. Now, what I'm going to discuss in this talk is actually not to characterize your input field, but instead to look at the property of the atoms which are ionized. So let me now focus on the Rabi technique, which we are using in our experiment, which is an interferometric technique. The Rabi technique, Rabbit means reconstruction of attosecond beating by interference of two photon transition. It's really a quantum interferometric technique. If we, to start with, consider ionization of an atom by a train of attosecond pulse in the frequency domain, a spectrum of high order harmonics, then you would detect electrons at certain kinetic energies. And these peaks here are separated by twice the laser frequency, since we have odd order harmonics. Now, if we add small fraction of the laser, which is actually used to generate the harmonics, so you, in the time domain, this is the field, then you can have absorption or emission of laser photon in addition to the absorption of the high order harmonics, and you get sidebands. And you see that these sidebands can be reached by two paths, a path corresponding to absorption of one harmonic plus a laser photon, or absorption of the next harmonic and emission of a laser photon. So there are two paths to reach the same final state. In quantum mechanics, we add amplitudes and not intensities. So we have an interferometer. Now to see interference, you need to vary something in one of the arms. And what we vary here is the time delay between our attosecond pulse train and the infrared, the laser field. We do that in an optical interferometer, such as the one shown here. This is a Mach-Zehnder type of interferometer. In one arm, our pump arm, we generate harmonics in a gas cell. We obtain pulse train. We filter this pulse train. We remove the fundamental field and actually the low order harmonics. And, and we have a probe arm where we have a delay stage. And then we recombine the radiation and focus the radiation into a vacuum chamber where we have the gas that we want to study. And here in the first experiment I'm going to show you, we use a magnetic bottle electron spectrometer provided by the group of at Göteborg University, collaboration with Raymond Pfeiffer and his group. And we measure the energy of the electron. We collect all of the electrons. So we have no angle resolution in this experiment. And of course, we vary the delay between the infrared field and the attosecond pulse. So let this slide show you a rabbit trace. This is the photo energy spectrum, the electron spectrum in color as a function of photon energy, or sideband order here as a function of delay. And you should focus on the signal of the sidebands, which oscillates very nicely at a frequency equal to twice the laser frequency. Now, this equation here represents the interference equation, and the information is really included in this phase offset of the oscillation and how this phase vary spectrally over the whole spectrum. So let us look at this phase. This phase actually includes two contributions. We can write this as a delay by dividing by the periodicity of the oscillation. We have a contribution from the XUV source. If you look at our quantum interferometer here, the signal that you get here is going to depend, or the oscillation depend on the phase of the different harmonics. And this leads to this delay, which is nothing else actually but the group delay of the attosecond pulses. And then we have a term coming from the ionization process, which contributes with a certain phase, so that we have this phase minus this phase here. So we have a delay here related to atomic ionization. This atomic ionization delay, which I'm going to discuss in this talk, can in turn be written as the sum of two terms. One, which is due to the one photon ionization process. It's also called Wigner delay, since it was introduced by Eugen Wigner. I'll come back to that in a moment. And then there is a second term, which is called continuum transition delay, and which is related to this continuum transition that we have here, and which are needed in order to have this interference. So you can consider this as really a correction due to the measurement. Our measurement, the goal of the measurement is to determine the phase of the photoionization process. We need to have this interference, and we need to have this absorption or emission to get this same final state and to get our interferometric measurement. This contribution is often small when at least at high photon energy, and especially it's very much independent of the atomic system, weakly depending on the angular momentum of the transition. So very often you can simply estimate this contribution. So let me now focus on the Wigner delay, give you an interpretation of this delay. I'd like to make an analogy here with optics, with ultrafast optics. The group delay of the electron wave packet, as it is ionized, is very similar to the group delay of a light pulse as it propagates through a material with a certain dispersion. Here, in the optics case, this propagation through a material, and in the atomic physics case, it's propagation in the potential, leading to a group delay equal to actually the derivative of the scattering phase in the case of one channel. And again, this delay was already introduced by Wigner in 1955. So in ultrafast optic, if you know the spectral intensity of your pulse, and if you know the group delay, then you can reconstruct the temporal properties of the pulse, the electric field of the pulse within an absolute phase, of course. Similarly, if you know the cross-section of the photoionization process as a function of XUV frequency, and if you know the Wigner delay, then you can reconstruct in the time domain your photoionization process. And this is really the motivation behind this work. So I'm now coming to the first example, how we apply this technique. And I'm going to show you a rather difficult phenomena, a complicated phenomena, which is a photoionization of xenon, not in the outer shell, but in the 4D shell, which is just below. So the question is really, what is the dynamics of the photoionization process? What happens when you shine xenon when you with XUV radiation? So what do we know from previous studies using synchrotron radiation? First of all, we know that above the edge, the 4D edge, you have not a decrease in ionization with photon energy as you have in hydrogen or helium, but you have a kind of delayed resonance. This is called a giant dipole resonance. So the threshold is approximately here, 70 eV, and then you have a really broad resonance. which has been interpreted with a collective effect of in the 4D shell. What else do we have? Well, we have, when you ionize xenon in the 4D shell, you can leave the ion in different spin orbit states. And especially around threshold, you have an anomalous branching ratio between the spin orbit channels at threshold. As you can see on this graph, the statistical branching ratio should be 1.5. You have that here, but here you have really something that happened at threshold, which indicates some effect of the spin orbit interaction. And finally, there is also Auger decay. When you create a hole in the 4D shell, electrons in the n=5 shell can fill the hole, and then another electron in the n=5 shell can be ionized and leads to an Auger electron. So when you ionize xenon in the 4D shell, you get a photoelectron and an Auger electron. So now let's do experiments. So the complexity requires that we do a coincidence measurement, measuring actually the pair of electrons, photoelectron and Auger electron. And this is an experimental coincidence map that is obtained. In this experiment, we use a titanium sapphire laser, 800 nanometer wavelengths. We generate harmonics in neon, and then we use these harmonics to ionize xenon in the 4D shell. And this is a coincidence map showing Auger electron on the vertical scale, and then as a function of photoelectron. And if you first look at the picture on the left, this is obtained with XUV only, you see a few islands corresponding to electron, to pair of Auger electron and photoelectrons due to absorption of, for example, here, harmonic 57 or 59 or 61. And the horizontal lines correspond to a certain Auger line. So this is, for example, the electrons due to absorption of harmonic 57 and with the Auger electron corresponding to this line here. Now, if you add the infrared field, you have additional islands, which are the sidebands. And these islands are in between the islands that we have seen before. So our experiment consisted in measuring these coincidence maps as a function of delay between the attosecond pulses and the infrared pulses. Now, the first information that we got is that there was not much difference between the oscillation that we were seeing for the different Auger lines. So in our conditions, it seems that the Auger process is not related to the first photoionization process. It does not influence the delay. So let me now concentrate on the photoelectrons. And here is the main experimental result showing the time delay of the photoelectron as a function of photon energy for the two spin orbit states. So what you see is that, and the calculations shown here have been obtained by using relativistic random phase approximation. And this is a calculation performed by Eva Lindroth at Stockholm University. So what you see is that the two results look the same here at high photon energy. You see a positive time delay and rather broad behavior and short time delay. And then at threshold, then there is something happening. Then the two curves do not look the same. And actually the delay becomes very large, more than 100 attosecond, and here it varies differently, but also being very large. So how can we interpret what we see? So here again, difference at threshold and rather long delays. So in order to interpret what we see, I'm going to show you a time frequency representation of the interaction. So here we use the calculation to do this analysis. We use the fact that we know the amplitude and the phase, or the delay, the derivative of the phase in frequency. So we know we can do a Fourier transform, and we have both the amplitude and phase as a function of time. And we can even do some time frequency analysis of the process. And we do that using the Wigner representation, showing here. This is the definition of the Wigner function, which is some kind of autocorrelation function of the complex amplitude of the process. And what you see in this Wigner representation, you see obviously two features. First of all, a very broad feature in this energy region, which corresponds to this broad, this giant dipole resonance, which I mentioned previously. And this feature has a width of a few tenths of attosecond and a very broad bandwidth of 50 electron volts. So it's maximum at 100 eV, broadband duration of few tenths of attosecond. And one can actually correlate this feature with the behavior of the effective potential that the 4D electrons see as it is ionized, with with a rather small potential barrier here. So the lifetime is very short. The second feature is what is happening at threshold. This feature here, narrow resonance at threshold with a long time delays, few hundred of attosecond, and a narrow bandwidth of a few electron volt. And again, you can relate that to a much smoother variation of the effective potential with a long potential barrier, so that the lifetime of the electron is much longer. And in between, you have interference between these two processes. So in summary, we can identify here this giant dipole resonance, short lifetime, broad bandwidth, at threshold, narrow resonance, which probably has to do with some relativistic effect and probably spin flip, which explain the narrow resonance and short lifetime. Now let me move to the second topic, which is look at photoionization of helium close to an autoionizing resonance. So we look at the well-known 2s2p resonance in helium, and this is a problem which has been described theoretically by Hugo Fano in 1961, and then studied by several groups, the group in Heidelberg and as well as in Saclay. And this process, so here we have a discrete state which is embedded in a continuum. So this is again a quantum interferometric type of process. You can reach this state in the continuum either by direct photoionization or by ionization, by excitation to the discrete state and then autoionization. This has been described and parameterized by Fano, and this is the behavior of the cross-section of this process as a function of a reduced energy, epsilon here, and the asymmetric parameter which characterize the interference. And this is the cross-section here as for different asymmetry parameters, and you see how the shape depends on this parameter here. Now, in parallel to this change of the cross-section, you also have change in phase and actually a change of pi of the phase. So although the cross-section behavior had been studied for many, many years, thanks to this interferometric technique using attosecond pulses, we are now in position where we can really measure the phase associated to a Fano resonance. So let me now show you some experimental results. So I'm going to show you first what we see by looking at sideband 38. So again, we have our quantum interferometer here. We analyze the phase. Actually, we are going to analyze here the phase due to the autoionizing resonance by looking at the interferometric signal on the sideband 38. So let me show you the results. And this is a result obtained recently. You can find detail of the methods in this article, but what I'm showing you is actually not published. This is obtained with very high spectral resolution. We use a very narrow bandwidth for the probe pulse in order to be able to measure this amplitude and phase with the best spectral resolution possible. So what you see here is the amplitude in red and the phase in blue. And you see indeed that we see a very strong interference in the amplitude and a phase jump of more than 2 radiant for the phase. And we can, similarly to the xenon problem, once we have the spectral amplitude and phase, we can determine the temporal amplitude and phase, and we can even do a time frequency analysis of the process, giving us the dynamics of the process. And let me show you a Wigner representation of this autoionizing process. And here you see several features. There is first an horizontal feature here, rather broad in frequency and short in time. This corresponds to direct photoionization. And then we have a vertical feature, which is correspond to autoionization via the discrete state. And there are strong interference between the two processes. This blue part here corresponds to a negative part of the Wigner distribution. We can look at this process by also looking at sideband 40. Let me just show you this result as a teaser and showing you where we are going and what we are doing at the moment. So what happens where we look not at sideband 38, but 40, this is what we get. And you see that in this case, the black line here represents calculation. And you see that we don't see the same phase jump, reduced phase jump, and we don't see a so clear interference for the amplitude. So there seems to be a loss of coherence of the electron wave packet that we measure. So the question that we are asking ourselves at the moment is how to characterize this possibly partially incoherent wave packet, and the possible interpretation here of what is happening, and also the difference between sideband 38 and sideband 40 is it might be the influence of another discrete state, the 2p2 state, which is close to the sideband 40. This is a story to be continued. Let me now move to the last topic of this talk, which is, okay, photoionization of helium using short attosecond pulse train. And let me come back to this picture here. Laser-assisted photoionization was first used to characterize attosecond pulses, has been used a lot to study photoionization dynamics, exactly as I showed you. Now, maybe the third way to use this process is, but now let's not concentrate on attosecond pulses, not on ionization, but really on the attosecond electron wave packet. Can we control photoionization? Can we control our attosecond wave packet by controlling the attosecond pulses? And let me present to you an experiment where we do that, and maybe some details about the experiment. Here we use our optical parametric Chirp-Pulse amplification system with a wavelength of 850 nanometer, not much energy per pulse, less than 6 femtosecond pulse duration, so short pulse duration, high repetition rate, 200 kilohertz, and carrier envelope phase stable, which is important for the experiments. This is a scheme of the setup. We have very tight focusing in this experiment, and we use a system of gas jet and catcher here in order to have a high pressure in the interaction region. We have 5 bar, and we have an opening of 40 micrometer. And then we have, of course, an interferometer in order to do this laser-assisted photoionization. This is just a grating that we can use to look at the spectrum. And then we focus again the pulse train and the infrared radiation into a chamber where we put some gas. Now, the interest of this system here is that, first of all, it has a very high repetition rate, and then it has a short pulse duration, and it is phase stable. And actually, using this system, we have only a few attosecond pulses in our train, and we can switch, we can control, we can decide whether we want to have mainly 2 attosecond pulses or 3 attosecond pulses. Now, the chamber that we put besides this setup is a reaction microscope or cold streams. So this is actually the French variant of these detectors, which is called CL. And the interest of these detectors is that you can really measure using coincidence technique the 3-dimensional electron momenta of the photoelectrons. So I'm going to present to you angular distribution obtained by, so we detect 3-dimensional electron momenta. I'm going to integrate over the azimuthal angle here, phi, and to present to you this angular distribution as a function of angle theta. And the polarization of the laser is in the vertical direction here. So first, let me show you the results with XUV only. And here what we have is the photoelectron spectrum as a function of energy and angle. And here we use harmonics generated in argon, and we photoionize helium. So we see 3 or 4 peaks corresponding to ionization by harmonics 21 to 25. So here there is no surprise. We see a perfect symmetry between the electron emitted upwards or downwards. And we see that we have peaks corresponding to absorption of these different harmonics. Now, what happens when we put the infrared field? And first, let's consider the 3-pulse case. So here, we expect to see sidebands. We do see sidebands, but only as you see here, in the down direction. So no sidebands visible in the up direction. So what is the reason for this asymmetry? Well, we think that what we have is an interference effect, that actually in this condition, the peaks are very broad, much broader than in this case. We are maybe in this situation, and there is some spectral overlap between 1 and 2 photon ionization, leading to interference effect and mixing, parity mixing. And since the phase difference depends on the product P dot A, depends on the direction of emission of the electron, this explains why the spectra look different in the up and down direction. What happens when we have only 2 pulses? Then, was also a surprise, no sidebands, but instead we have a shift of the peaks, as you can see here, and a shift which is actually different in the up and down direction. The peaks move in this direction, in the up direction, inwards, while the peak move outwards in the down direction. How can we understand that? Again, let me talk about interferences, but this time in the temporal domain. So making an analogy with interference, diffraction through a pair of slits. We look here at two pulses, and which these are 2 electron wave packets in the time domain. To go to the frequency domain and making a Fourier transform, as you know, we have 2 pulses. We get an interference pattern in the frequency domain, and this is what we see. Now, what happens when we add the infrared field? What happens is actually you phase shift one of the pulses relative to the other. And this, if you have a phase shift on one of your slit, then you get a shift of your interference pattern, as is well known, for example, when you think about double slit experiment. Now, in addition, this phase shift depends on the momentum of the electron, so it will be opposite if you in the 2 direction of emission. In addition, this phase shift depends on the momentum, so that actually the shift increases as the energy of the photoelectron increases. So we think that we can describe this phenomena using this time slit interference interpretation. So finally, you wonder, oh, what happens when I vary the delay between the infrared field and the XUV field? Well, these are the results. On the top are the experiments, and on the bottom are simulations using a strong field approximation method. And what you see in the 2 pulse case, you see some oscillations, so no sidebands, but oscillations. So you see it's a little bit like a streaking trace, but it's for each harmonic components. In the 3 parts case, then you have instead some kind of rabbit type of result, but with the difference that this time it's very asymmetric. So what is shown here is the up result. As you see, the periodicity now is omega and not 2 omega as in traditional rabbit. Again, the experimental results are a little bit noisy, so we're presently working on improving the statistics of our experiment in order to study this phenomena in better. So with this, I would like to conclude this talk, and I would like to thank you your attention, and also thank all of my colleagues in Lund working on these experiments. On the top part, you have the postdocs and the more senior researcher here, Cord. Arnold, Mathieu Gisselbrecht, and Per Eng Jonsson. And in the bottom line, you have all of the postdocs working on these different experiments. So thank you for your attention.
Thank you so much for this really nice talk. We really appreciate you being here today. Now, are there questions, comments? Before we continue, I would like also to make an announcement that Professor Lilier's group in Lund also have a seminar series, which they have started to run. So do go to their website and check it out, because we are here also to support our other initiatives that are aligned with our motto, which is try to make science free and accessible to everyone, especially in these difficult times.
I want to say directly, it's not me, it's my younger colleagues that really organized this conference or symposium series. So yes.
Do have a look, yes. And it's also always a team effort. I also have to thank very much Cornelia Hoffman and Abby Bray for organizing this, because it is really hard work. And we have our first question from Mathis Janssen. Thank you for your presentation and very impressive work. Could you explain again how is it possible to find the 0 point on the time axis and therefore differentiate 100 attoseconds from 0 attoseconds?
I would like to say that it is not possible to find the 0 on the time axis. You always measure differences. So if I go back to the picture, probably to explain this, so how do we put our scale? This is the question. Maybe I go back to this. We actually determine the 0 here or 100 by measuring at the same time photoionization in neon. Okay, so this is characterized using the neon result, where you can really assume that the photoionization time delays, if we remove the TICC contribution, is 0. So this is a difference. Actually, what this represents, this is a very, very good question. That what is represent here is the difference between the time delay that we measured in xenon 4D with the time delay in neon on the external shell, which is approximately 0.
All right, thank you very much.
If I want to, the TICC compensates each other, and the Wigner time delay for neon is 0. So this is time delay for 4D shell in xenon.
Okay.
Is that clear? Would you like to ask more? So anyone who would like to ask questions, do feel free to put them in the Q&A tab. From, I cannot see the name of, from, there is a question here. Thanks for your talk. I was wondering if the OGF photon in your xenon experiment absorbs an IR photon.
This is a very, very good question as well. Let me go back to the previous slide now. And yeah, here. Actually, yes. And you can see, not very much, but there are a few, you can see here, you can find a few, it's very, very weak. But there are a few line where you see a sideband of the Auger electron, but we could not see any oscillations. This is too small signal. I can also add that this experiment, which I show here, I think is the most difficult experiment in my lifetime. It took 3 years, and in the end, I mean, you can see here that our error bar are not that great. This is also an experiment I would like to redo with much better statistics. But anyway, yes, we do see a sideband of the Auger electron. The sideband that we have analyzed, which are here, correspond to the photoelectron.
Yeah, thank you very much. Here's actually Anne from Heidelberg.
Yeah, hello.
So, I'm so excited to, I don't know, you can't see me, but I was just so excited to see now these results. I didn't know that you published them last year. So yeah, that's why I know that you were thinking about the time delay of the sidebands of the Auger electron. So
yeah,
great work. And can I ask another question to your results? I was wondering, I think I did not really understand why the 4D3 3/2 and 5/2 phase delay is why is it that different? Can you explain this again?
I think well, first of all, they are similar in this region here.
Yeah,
but they are different at threshold. This is a very good question as well, because I think what you have at threshold is actually an interference between different channels, different relativistic channel, and when you have an interference effect, you can have a large variation, and this is what we see. So I'm not. Maybe I'm not answering very well this question, but this is my interpretation of about what happened.
Mm. Okay, and then I'm sorry, maybe this is now a stupid question, but why is the Wigner time delay in neon 0?
Because it's very small. It's not 0, but it is very small. So what we see in this result published a few years back by Isinger et al. What we see is really the tau CC delay, which is a negative delay and which varies like that. I don't know if you can see my hand.
Yeah, I see.
But this is the tau CC delay that we actually measure. The Wigner delay itself is approximately 0. The reason is that there is no potential barrier, or the electron just leave very fast. So in this case, xenon 4D, you have really a potential barrier which is trapping the electron more or less, depending on the configuration. But if you have nothing, just Coulomb potential, then it's very fast, and it's just a few attoseconds.
Yeah. Okay, yeah, I wasn't clear. So this means, but for the heavier your atoms come, or the lower you come from the atomic table, the larger the Wigner delay needs to be, right?
That really depends on the photon energy, on the configuration, on many things. But yes, I think in helium neon, using XUV radiation from the harmonics, this is very small, and what has been measured in the experiments has been this tau CC delay, which which is a delay due to the electrons in the actually infrared field.
Yes, yeah. Can I ask another question? I was just wondering one small detail. You said that for the experiments, you reduced the bandwidth. So are you now, it's not 10 nanometer, it's actually even more narrow band?
In these experiments, this is more. This is like 50. In the helium experiment, it's about 10 nanometer. Okay. So we reduce from normally 70 or 50 to 10 nanometer in the helium experiment, the second helium experiment.
Yeah. I meant, thanks a lot.
So thank you. We have another question from Abdelmalek Tawoutui. First of all, he is thanking you for your nice talk, and he would like to know if the rabbit technique can be used when also the probe laser is contributing in the ionization process.
The infrared field is also contributing in the ionization process. Otherwise, this would not. But you mean if you Yeah, I think the rapid technique cannot be used the way we are using it if the infrared field is too strong, which means if you switch off your XUV radiation and the intensity of the infrared is enough to have multiphoton ionization, for example, then it's complicated, I would like to say, and you have lots of interference everywhere. So the answer is no, you should keep the intensity of the infrared weak in order, at least in order to do all the analysis that we do.
Is that clear, or would you like to ask further? Okay, seems clear, but feel free to unmute yourself if you would like to speak. And there's one question from Andrew Brown. Is it just speculation that the large difference between the 5/2 and 3/2 time delay is due to interference between channels, or is that picked up in your theoretical calculations?
This is picked up in the theoretical calculation. I could show you a slide, but I don't have it at the moment. But you can look in our article, which is in reference here, in this article published this summer, 1 year ago, last summer. Then there is a picture showing the interference between the different relativistic channels. So it's based, of course, it cannot be obtained from the experimental measurements alone. It's based on the calculations. Yes.
So Cornelia Hoffman is making me aware that there's another question in the chat. Cornelia, feel free to bring it up.
Yes, I just, Andrew is also there. Is the answer okay for you, Andrew, or do you want to follow up?
Oh, that was perfect. I have the reference. Thank you.
Okay, thanks. Right, yeah, I'm also monitoring the chat. There's a question from Xiaosong Chu. Thank you for your talk. I have a very basic question. Why is gas jet used in the setup in the third work and gas cell is used in the previous works? Could you comment on the main difference between the two setups?
This is a very good question. I could talk 1 hour on just on this. I think that the reason is I just want to go back to here. Here it's very difficult to, we have a tight focusing geometry, and phase matching tells us that you need to have a high pressure and a short interaction medium. You can also derive that from actually the scaling laws that I presented at the beginning of the course. Maybe I go back to that very rapidly here. Oof. So if you go from so if you have a certain condition where you have certain loose focusing geometry, and then you go to tight focusing geometry simply because you need the intensity of in the medium, and you have only 10 microjoule, you can still reach 10 to 14 watts per square centimeter that you need by using tight focusing, 5 centimeter focusing in our case. But then, in order to have to keep your conversion efficiency reasonable and the same as before, you need to have a small medium and a high pressure. And this is impossible to have with a cell. So this is why we have a jet with a very small aperture and a high pressure. So in a more normal case, you can use it, but it's more difficult to have long jets. So this is why we use often a small cell or cells, but less pressure.
Oh, okay. Yes, thank you very much.
Okay, thank you. I have one question as well. I realized you are using a lot of Vigna functions to track resonances and to look at what is going on. One question I have is because in the past you have used a lot of standard time frequency analysis using, for instance, windowed Fourier transforms like Gable transform and these kinds of things. Why is the Vigna quasi-probability distribution better to track this kind of effect?
I'm not sure they are better. What I like with the Vigna distribution is that you can see the interference very well. And it's a little bit, brings us closer to maybe quantum optics. Although it's a bit different because it's not momentum and space, it's time and energy. So, but I'm not sure we get so much more information than using wavelet transform or Gabor transform. I'm not very sure. I would say similar.
Yeah, because I know from the quantum optics people that they always choose the quasi-probability distributions depending on what they are looking for. Hence the question.
Yeah. I mean, we are going, if I can speculate a little bit, at least in Lund, we are thinking a lot, some of us, towards actually really measuring more the properties of the electron wave packet as quantum objects, not as optical waves or electron waves, but really keeping, we are kind of assuming that everything that we produce is coherent. Is it always the case? Question mark. I don't know. Probably not. So we're a little bit going in this direction, and the Wigner distribution is a help to discuss these things. Mm-hmm. For example, if I go to the to this case here we have a, here we think this is a very coherent wave packet that we create, showing this very sharp phase jump and interference process. Very nice Wigner distribution with a lot of interference. If we look at this one where you have obviously reduced coherence, then if we plot, I don't have it here, the corresponding Wigner distribution, you see a huge difference with the previous one, much less interference. So maybe we can learn something from this. But this is a little bit work in progress.
Thank you very much. It's really interesting. That plot is also absolutely beautiful, the one of the funnel resonance. And it's interesting also that you can see the different pathways.
Yeah. Thank you.
It's absolutely amazing. Thank you. So is there anybody else who would like to ask questions? Do feel free to ask. We are going offline pretty soon. As we know, some people like to ask questions off record. So for those who are watching on YouTube from across the globe, huge thanks for supporting the initiative and for watching us today with the Atto Fridays Seminar Series. And thanks as well to Professor Louis for the really nice talk and for joining us today.